Wildcat. So we're going at 3. Return of the inverse. Logarithmic functions. Warm up. For each function, determine the domain and range. Describe the function as exponential growth or decay when x is greater than 0. Number 1. When f of x equals e to the x, the domain is negative infinity to positive infinity. The range is from 0 to infinity, not including 0, and it's exponential growth. 2. When g of x equals e to the negative x, the domain is negative infinity to positive infinity. The range is from 0 to infinity, not including 0, and it's exponential decay. Let's take a look at the next page. Getting started. Consider the table and graph of the basic exponential function f of x equals 2 to the x and its inverse. All right, so we have f of x equals 2 to the x, and that is this graph right here. Okay, and then we have the inverse, which is right here. Go and look over the graph of f of x and f inverse of x. Let's take a look at number 1. Complete the table to identify the key characteristics of each function. Compare the key characteristics of the function and its inverse. Go ahead and read and complete the table. Let's take a look at the next page. Activity 3.1. Logarithms are exponents. It is necessary to define a new function in order to write the equation for the inverse of an exponential function. The logarithm of a number is the exponent to which the given base must be raised in order to produce the number. If y equals b to the x, then x is the logarithm and can be written as log base b of y equals x. The value of the base of a logarithm is the same as the base in the exponential expression b to the x. For example, the number 3 is a logarithm to which base 2 must be raised to produce the argument 8. The base is written as a subscript 2. The logarithm or exponent is the output 3. The argument of the logarithm is 8. Go ahead and look over the worked example. All right, let's take a look at the next page. Number 1, analyze the exponential equation y equals b to the x and its related logarithm equation log base b of y equals x. State the restrictions, if any, on the variables, explain your reasoning. Go ahead and read over and complete the table. You can use a triangle power to help you think about logarithms. All right, go ahead and look over the worked example. All right, let's take a look at the next page. Number 2, draw triangles of power to illustrate each equation, then rewrite in exponential form. Go ahead and look over 2a, b, and c. All right, let's take a look at activity 3.2, graphing logarithmic functions. Recall that the logarithm of a number is the exponent to which the given base must be raised in order to produce the number. If y equals b to the x, then the logarithm is written as log base b of y equals x, where b is greater than 0 and b does not equal 1 and y is greater than 0. A logarithmic function is a function involving a logarithm. What do the graphs of logarithmic functions look like? Number 1, the graph of h of x equals b to the x is shown. Sketch the graph of the inverse of h of x on the same coordinate plane. Label the coordinates of points on the inverse of h of x. Okay. So here is h of x. And here's the graph right here. Now, whenever you talk about inverses, you need to graph f of x equals x, because if they're inverses, they reflect over the f of x equals x line. Okay. Now, when they're inverses, these values switch. So this becomes 1 divided by b squared negative 2. Okay. 1 divided by b, negative 1. Zero, 1 becomes 1, 0. and then and b squared 2. And then there's your inverse. All right, go ahead and finish up number 1. Let's take a look at the next page. 2. Write the equation for the inverse of h of x equals b to the x. All right, so to do that, we have h of x equals b to the x. We first change h of x to y, so y equals b to the x. And then for the inverse, you switch x and y. So x equals b to the y. And then we need to take log base b to both sides. Now, log base b of b, they cancel each other, so you're left with log base b of x equals y. So, h inverse of x equals log base b of x. All right, go ahead and finish up number 2. All right, number 3. Do you think all exponential functions are invertible? If so, explain your reasoning. If not, provide a counterexample. Yes, all exponential functions are invertible because all exponential functions will pass the horizontal line test. Logarithms were first conceived by a Swiss clockmaker and amateur mathematician Jos Berg, but they became more widely known and used after the publication of a book by Scottish mathematician John Napier in 1614. Tables of logarithms were originally used to make complex computations in astronomy, surveying, and other sciences easier and more accurate. With the invention of calculators and computers, the use of logarithm tables as a tool for calculation has decreased. However, many real-world situations can be modeled using logarithmic functions. 2 frequent used logarithms are logarithms with base 10 and base e. A common logarithm is a logarithm with base 10 and is usually written without a specific base. A natural logarithm is a logarithm with a base e and is usually written as ln. All right, let's take a look at the next page. 4. The function p of x equals log base 2 of x and q of x equals log base 3 of x have been graphed for you. Okay, let's go ahead and graph those in Desmos first. So we're going to do, now to get log, we're going to need to go here, functions, and I think you have to scroll almost all the way down to the bottom, and then probably scroll back up. There you go, log base 2 of x is here, and let's go ahead and graph that in red. Okay, and then let's go ahead and graph log base 3 of x. Let's go ahead and graph that in black. Okay, so this is in red. This is in black. So now let's graph c of x equals log of x. Okay, so functions. Now, if it's log, it's assumed base 10. So log base 10 of x. Let me try that again, see if it graphs it in a different color. Doesn't help us if the line is in red. There we go. So let's graph that in blue. Now you'll see that one's below the first two. And then let's graph natural log of x. Oh, don't want that one. Happens, just delete and go back. Log of x. And you can see it's just slightly above log base 3 of x, and let's graph that in purple. All right, go ahead and finish up the graph. All right, mark out B. The teacher explained 4C, 4D, and 4E on a separate piece of paper. All right, let's take a look. For C, analyze the characteristics of P of x, Q of x, C of x, and N of x. P of x equals log base 2 of x. The domain is 0 to infinity, not including 0. The range is negative infinity to positive infinity. The x-intercept is 1, 0. There is no y-intercept, and the vertical asymptote x equals 0. Q of x equals log base 3 of x. The domain is from 0 to infinity, not including 0. Range is from negative infinity to positive infinity. X-intercept is 1, 0. There's no y-intercept, and the vertical asymptote is x equals 0. C of x equals log of x. The domain is from 0 to infinity, not including 0. Range is from negative infinity to positive infinity. X-intercept is 1, 0. There's no y-intercept. The vertical asymptote is x equals 0. N of x equals natural element of x. The domain is from 0 to infinity, not including 0. Range is negative infinity to positive infinity. X-intercept is 1, 0. There's no y-intercept, and the vertical asymptote is x equals 0. All right, let's take a look at the next page. 4D. What is the inverse of logarithm function c of x equals log of x? Now, first step is change c of x to y. So you get y equals, we need to include the log base 10 of x. And then next step is you switch x and y. So x equals log base 10 of y. And then we need to raise both sides by 10. Now, 10 log base 10 of cancels. So then you're left with 10 to the x equals y. So c inverse of x equals 10 to the x. All right, go ahead and finish it up. Take a look at the next page. 4e. What is the inverse of logarithmic function n of x equals ln of x? So first step, change n of x to y. So y equals natural log of x. And then for inverse, you switch x and y. So x equals ln of y. And then we're going to raise both sides by e. Okay. E to ln cancels, so you're left with e to the x equals y. So n inverse of x equals e to the x. All right, go ahead and finish up 4e. All right, let's take a look at the next page. Activity 3.3, applying logarithms. The Richter scale is used to rate the magnitude of an earthquake or the amount of energy released. An earthquake's magnitude m is determined using the equation m equals log of L divided by L naught, where L is the intensity of the earthquake being measured by the amplitude of a seismic reading taken 100 kilometers from the epicenter of the earthquake, and L naught is the intensity of a standard earthquake or threshold quake whose seismic amplitude is 10 to the negative 4 centimeters. Number 1, write an equation to model the magnitude of a standard equation. M equals log of L naught divided by L naught equals log of 1, which equals 0. 2. An earthquake in California measures 6.8 on a Richter scale, while an earthquake in Japan measures 7.2. Use technology to determine how many times more intense the Japanese earthquake was than the California earthquake. Step 1. Solve the California earthquake equation 6.8 equals log of x divided by 0.0001 graphically. So let's go ahead and do that. Okay, so to do that, we're going to graph first y equals 6.8, and then we're going to graph okay. Now we need to zoom out till we find the point of intersection. So that is 600, let's round that to a whole number, 631. Okay. Now, step 2, solve the Japan earthquake equation y equals 7.2 equals log of x divided by 0.0001 graphically. Okay, so let's go ahead and do that. Now, all we have to do is change this to 7.2. And then I'm going to go to home screen, and then I'm going to zoom out again. Now, you keep zooming out. Eventually, the point of intersection will pop up. And there it is. And let's go and round that to 1585. Okay. Step 3, divide the Japan earthquake intensity by the California earthquake intensity. Okay. So let's go ahead and do that. And we probably want just Desmos scientific calculator. So 1585 divided by 631 is, let's go and round that to be 2.5. The Japanese earthquake was 2.5 times more intense than the California earthquake. All right, go ahead and finish that up. Let's take a look at the next page. Go ahead and mark this page out. Talk to talk, getting into a logarithm. Number 1, identify the key characteristics for the exponential and logarithmic functions to complete the table. All right, go ahead and complete the table. All right, let's take a look at the next page. The student works 1, 2, 3, 4, 1A, 1B, 1C, 1D, and 2A. All right, let's take a look at the next page. The student works 1, 2, 2A, 2B, 2C, and 2D. All right, go and start working on your assignment and have a wonderful Wildcat day.